Let's see the question. The common base current gain of the PNP bipolar transistor is 0.99. The common emitter current gain of the transistor is. So if you see, he has given the common base current gain alpha is equals to 0.99. He's asking what is beta. That is a common emitter current gain. If you see, this is the common base transistor. Input is at the emitter, output is at the collector. The input junction is usually forward biased. This is the NPN transistor. If you see, input junction is usually forward biased, output junction is usually reverse biased. So it is like this. So when the output junction is reverse biased, there will be a small leakage current that will be IC naught or ICB naught. So the overall collector current that flowing is, the overall collector current is nothing but alpha IE, that is nothing but alpha times of input current plus IC naught. This is the current gain equation of, this is the collector current equation of the common base transistor. If you see similarly for the common emitter, for the common emitter transistor, input is at the base, output is at the collector. This is the collector. Input junction is forward biased, output junction is reverse biased. So there will be a small leakage current flowing here also between the collector and emitter terminal, that is ICE naught. ICE naught. This is ICB naught or IC naught. So the overall collector current that is flowing here is the collector output current is nothing but the current gain times of input current, that is beta IB plus ICE naught. This is the collector current equation of common emitter configuration. Now we'll see the differences here. If you derive the equation here for the common base, if you derive IC is equals to alpha times of IE. IE can be written as the emitter current is nothing but the sum of collector and base currents plus IC naught. So IC is equals to alpha IC plus alpha IB plus IC naught. So here if you take IC common, 1 minus alpha is equals to alpha IB plus IC naught. So the overall collector current IC is equals to alpha divided by 1 minus alpha IB plus 1 by 1 minus alpha IC naught. This is the equation in terms of alpha. Similarly, if you see this equation, IC is equals to beta IB plus ICE naught. If you compare equation 1 and 2, this is equation 1 and this is equation 2. By comparing, you will get, by comparing these two equations, by comparing 1 and 2, you will get beta is equals to alpha divided by 1 minus alpha and ICE naught is equals to 1 divided by 1 minus alpha times of IC naught. Okay, this is the comparison and equation. So this it can also be written as ICE naught, can also be written as 1 plus beta times of IC naught. Okay, 1 by 1 minus alpha is nothing but this component. You can replace this component with 1 plus beta also. So this is the relation. So if you follow this relation, beta is equals to alpha divided by 1 minus alpha. Substitute the values 0.99 divided by 1 minus 0.99. So beta value will be approximately 99. So answer is option C. We'll see the next question. Like the video, share the video, and subscribe to the channel for better content and more videos. Determine the change in collector current delta C due to the change in base emitter voltage VBE from 25 degrees to 100 degrees centigrade for the silicon transistor in a fixed bias configuration having beta is equals to 100. Consider the following variation in the silicon transistor parameters at a temperature T is equals to 25 degrees, VB is 0.65. At a temperature T is equals to 100 degrees centigrade, VB is 0.5 volts. So this is the most important parameter. Given things are, what are given to us? Beta is equals to 100 and at a temperature at T is equals to 25 degrees centigrade, VB is 0.65 volts. At T is equals to 100 degrees centigrade, VBE, the base emitter voltage is 0.5 volts. Fine. Now we'll try to find out the difference in the collector current. Before that, we have to apply the input KVL. So if you apply the KVL at the input terminal, if you apply the Kirchhoff voltage law at the input terminal by applying KVL at input terminal, input loop. We have to say it is an input loop. We will get the equation VCC is equals to IB base current RB plus VBE. So what is the base current? The base current IB will be VCC minus VBE divided by RB. So he's asking us to find out the differences in the collector current. So the collector current will be, the collector current is nothing but beta times of IB, base current. So what is the value of beta? Beta value is 100 and base current can be written like this. So 100 times of VCC minus VBE divided by RB. Now we will find out in two cases. This is case 1, this is case 2. In case 1, we have temperature T is equals to 25 degrees. VB is the base emitter voltage is given as 0.65. In the case 2, we have a temperature T is equals to 100 degrees centigrade. VB is 0.5 volts. Okay, VB is 0.5 volts. Now substitute these values. IC1 is equals to beta is 100 multiplied by VCC value is given as 10 volts. So 10 minus VB is 0.65 divided by the base resistance RB is 250 kilo ohms. So if you substitute this, you will get IC1 as 3.74 milliamps. Similarly, IC2 is equals to 100 multiplied by 10 minus 0.5 divided by base resistance 250 kilo ohms. So you will get IC2 as 3.8 milliamps. So the difference in collector current delta IC is equals to IC2 minus IC1, that is equals to 60 microamperes. So here the answer is option A. We'll see the next question. Which one plot gives the closest resemblance to the stability factor SIC0 of the emitter bias configuration of BJT with respect to RE divided by RB? So these are the graphs given to us. Now we'll solve the stability factor of the emitter bias. Emitter bias is equivalent to the potential divider method. It is almost equal to potential divider method. First we'll see the circuit and we'll derive. See, this is the circuit for us. This is R1, R2, transistor, the emitter resistor, and this is a collector resistor. This is ground and this is VCC. Now if you see the equivalent circuit of this, the equivalent circuit will be here the V Thevenins and here the R Thevenins. As usual, collector resistance RC and emitter resistance RE. This is VCC. So if emitter resistance is there, it can be treated as the emitter bias circuit. Okay. So if emitter resistance is there, it can be treated as emitter bias circuit. There is no need to get confused. So now what is V Thevenins? The V Thevenins is nothing but the voltage across R2. This itself is a V Thevenins. You can call this as a VB also or VB. Similarly, the R Thevenins is nothing but R1 parallel with R2. You can call this as RB also, the base resistance. Okay, you should not get confused. So V Thevenins, here I am writing, the V Thevenins is nothing but VCC divided by R1 plus R2 multiplied by R2. It is the voltage across R2 resistance. Whereas R Thevenins, which can also be called as base resistance RB, is equal to R1 parallel with R2. Now apply the KVL at the input loop. If you apply the KVL at the input loop by applying Kirchhoff voltage law at input loop, we will get the equation V Thevenin is equals to base current IB, RB or R Thevenin both are same. IB, RB plus VBE plus VE, emitter voltage. The emitter voltage can also be written as emitter current IE multiplied by RE. So this V Thevenin, I am writing it as IB, RB plus VBE. The emitter current can be written as a sum of the base and collector currents multiplied by RA. So if you simplify this equation, you can write the base current taking common. It will be like this. IB can be taken out plus RE plus ICRE plus VBE. I have just taken common this RB parameter. This IB I have taken common. Okay, this is the final equation. So now what is the stability factor? The stability factor can be given as stability factor formula S is equals to 1 plus beta divided by 1 minus DIB, the rate of change of base current with respect to collector current, IC, DIB by DIC. This is the stability factor formula. So we need, beta is the constant here. So we need to find out the DIB by DIC for this emitter bias circuit. So differentiating the above equation with the DIC. So with that we can find here V Thevenin is the constant parameter, so it becomes 0. DIB by DIC remains like this. RB plus RE. This IC becomes 1 because the differentiation of IC with respect to IC is 1. So RE is the constant, that remains same. VBE is the constant, that remains 0. So here DIB by DIC is minus RE divided by the base resistance RB plus RE. This is the value. If you substitute this value in the S, you will get the stability factor is equals to 1 plus beta divided by 1 plus beta, the emitter resistance RE divided by RB plus RE. So now if you simplify this parameter S can also be written as 1 plus beta divided by 1 plus beta. If you simplify this, it will become 1 divided by 1 plus RB divided by RE. If you take RE out and cancel, this will be the equation. So now if you look at this factor, this particular factor, if RB is far less than RE, what happens? The stability factor will be closer to 1. Now based on this, you see the diagrams. So the stability factor, here the stability factor, if reverse happens, if RB is far greater than RE, or RE becomes emitter resistance becomes 0, then stability factor will be closer to 1 plus beta. With this equation, if you see, if RE increases, RE becomes 0, what happens? The stability factor will become 1 plus beta. If RE is very, very high, the emitter resistance value is high and base resistance is low, then stability factor will be closer to 1. Based on this, you see, which is the answer? So here in this case, RE by RB, emitter resistance by base resistance ratio is very high. So here RE is lesser than, RE is far greater than RB. So stability factor S is equals to 1. So this is correct. Answer is option B. Like the video, share the video, and subscribe to the channel for better content and more videos. Now we'll see the next question. A BJT is having the common emitter current gain 100. Consider the 10 volt VCC supply. The base emitter voltage is 0.7. What will be the value of collector resistance RC and RB to set the Q point? IC at 10 milliamps and VC at 8 volts. So now we'll try to calculate like this. So he's asking what is RC and what is the base resistance if the Q point IC and VC are equal to 10 milliamps and 8 volts. So this is a very good information. If you apply the Kirchhoff voltage law in the output loop by applying by KVL at the output loop, you will get VCC is equals to ICRC plus VCE. So substitute the values now. VCC is nothing but 10 volts. The collector current is given as 10 milliamps. The collector resistance is not known. VCE is given as 8 volts. So substituting these values, the collector resistance value RC will be equal to 200 ohms. Now similarly, so here the collector resistance is known. Now next we have to apply the Kirchhoff voltage law at the input loop by applying KVL at input loop. You will get VCC is equals to IB into RB plus VBE. Here we do not know IB, we do not know RB. So IB can be found. What is IB basically? The IB is nothing but IC by beta. So the collector current is 10 milliamps. The beta value is given as 100. So if you substitute, you will get IB is equals to 0.1 milliamps. So substitute IB value there. So VCC is 10 volts, IB is 0.1 milliamps. The base resistance is not known. The VBE is given as 0.7 volts. So by substituting these values, you will get RB is equals to 93 kilo ohms. So the base resistance RB is 93 kilo ohms, collector resistance RC is 200 ohms. So now the answer is option A. Let's see the question. The output characteristics of a BJT amplifier is given. Find the minimum collector current required for output impedance, that is output resistance R0 is equals to 50 kilo ohms. So this is the early voltage he has given, VA. Okay, this is the early voltage VA and these are the output characteristics. So if you observe carefully, when VCE is equals to minus VA, that is early voltage, the collector current becomes 0. Whereas when VCE is at lower values, means when VCE is far lesser than the early voltage, then the collector current will be higher. Okay, we have got a formula here. The early voltage is equals to 50 volts, that is given. So the output resistance R0 is equals to early voltage modulus of early voltage divided by collector current. So VA is the early voltage here. This is nothing but early voltage. So the output resistance is given as 50 kilo ohms. The early voltage is 50 volts divided by IC. Now the collector current IC is equals to 1 milliamp. So the answer is option A. In the circuit shown in the figure below, beta is same for both BJTs. Neglecting the early effect, I2 by I1 is. So this is nothing but a current mirror circuit. This is nothing but the current mirror circuit. So here beta 1 is equals to beta 2 is equals to beta. For both transistors, beta will be same. Similarly, the VB1 for transistor 1 and VB2 for transistor 2 will be same. That is equals to VBA. Both will be same. So if you analyze carefully, here the current flows and here the current splits. Okay. So I1 is the current, reference current that is flowing through the resistor R. Now, suppose the collector current of Q1 is IC1. Suppose the collector current of Q1 is IC1 with the base current IB1. Then for the transistor Q2 also, the collector current that is flowing will be IC2 with base current IB2. Both will be same because the transistors have the same beta value and same base emitter voltage value. So if you write the equation, current I1 that is flowing through the resistor R. Current I1 is flowing through the resistor R. So I1 is equals to, it will split into two parts, IC1, collector current of transistor 1 and the normal base. This is total base current. You can write this as IB. Okay. So it will divide into IC1 plus IB. This IB is nothing but the sum of base currents of two transistors. So IB1 plus IB2. So here the IB1 and IB2 both will be same. So I am writing this as 2 into IB2. Okay, 2 into IB2 because the IB1 and IB2 both are same. And I can write this I1 is equals to, see here IC1 plus this I can write 2IB1 or 2IB2. So I can write this as 2IB1 also, because the base current of IB2 and IB1 are both the same. Okay, IB1 is equals to IB2 is equals to same base currents. Okay, both are same. So now this IB1 you can replace this as IC1 divided by beta. Okay, so I1 is equals to IC1 plus 2 IC1 by beta. Similarly, you can write I1 is equals to this IC2 plus 2 IC2 divided by beta, whereas IC2 is given as I2. So I2 plus 2 I2 divided by beta. So now I1 is equals to I2 if you take out beta plus 2 divided by beta. So by simplifying this, I2 by I1 will be beta divided by beta plus 2. So the answer is option D. We'll see the next question. So next question is also similar to this. This is a current mirror circuit and asked in the ISRO examination. So here the same assumption will start. All transistors have same beta value and VB value, same beta and VB, base emitter voltage. So based on this assumption, we have to start. So this is the I reference that is flowing through the resistance R1. This I reference will split into the collector current here and the base current here. Okay, and this base current gets amplified and flows as the emitter current here. Okay, this is IES. Okay, this emitter current you can write it as IES because it is the emitter current of transistor QS. Now this IES will divide into two parts. One is the base current of transistor QR, IBR, and the next is a base current for all the transistors, Q1, Q2 up to Qn. So I'm writing this equation, IES, the emitter current of transistor QS. This is the transistor QS. Emitter current of transistor QS can be written as the base current of transistor QR plus the base currents of all the transistors up to N. Okay, hence all transistors have same VB value. The base currents will be same for all transistors. So this is of N number and this is additional one quantity. So now IES, the emitter current of QS transistor, can be given as N plus 1 base current. Okay, this base current you can write as a collector current divided by beta. Before that, we will assume that all the collector currents, that is I1 is equals to I2 is equals to I3 up to IN, all the collector currents will be constant, that is equals to I0. Okay, so now substitute this. IES is equals to N plus 1, the base current is written as I0 divided by beta. Now the base current of QS transistor, is nothing but the emitter current divided by beta plus 1. So here you can write this as N plus 1 I0 divided by 1 plus beta multiplied by beta. So now the reference current as we discussed here will split into two parts. One is this part, that is the collector current, which is I0. The other one needs nothing but the base current. So one is the collector current plus other one is base current IBS. So if you add these two, I0 1 plus N plus 1 I0 divided by 1 plus beta into beta. So now I0, the current I0 can be given as I reference divided by 1 plus, sorry, here I0 is taken outside, so there will not be any I0. So 1 plus N plus 1 divided by 1 plus beta into beta. So now the answer is option A. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma, and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.